Okay, hi everyone. Finally, here is the video on the Paris Metro that I have cared so much about and spent so much time preparing. Uh, if you take a look right here at this map, you can really see just how incredibly complex the entire Paris Metro network actually is. It is a massive system made up of about 300 different stations, and it spans across about 13 distinct lines that weave through the city. There's also the regional metro, this one with the thicker lines, the so-called RER. I'll tell you right away that I didn't cover this because, as usual, my interest is only to show the computer science aspects, MMH, related to this problem. What we are about to see is an application of graph exploration. A graph compared to the one we saw in the previous video about the traveling salesman in Sicily, which is extremely more complex in this case, with about 300 nodes, in fact. This graph, however, is not completely connected, meaning each node is not directly connected to all the others. It is an unweighted graph in this case because the edges connecting two nodes do not have a metric, they do not have a particular evaluation. And then anyway, it is symmetric, yes. This too is also symmetric in the sense that there are no particular characteristics in going from one station to another and vice versa. All right, and what is the problem we are about to face? Faced with a situation of this kind, we need to establish a path between two stations, therefore finding an itinerary. This time, not all itineraries are finding an itinerary between two specified stations. I'll tell you right away that the application I've prepared doesn't necessarily find the best itinerary. So the absolute best, the so-called optimal solution, but it does find a solution. Very often, thanks also to the type of network that has been designed in an extremely accurate way, now we will see a little bit what this definition consists of. It is not necessary, to make many changes. So the possibility we have with all these lines, with all these intersections, to limit the number of changes makes the work a bit simpler. However, there is always the issue of having to explore a graph. That is, you start from any station and you need to find another station within this map. I repeat, we are excluding the RER, these slightly larger lines that haven't been loaded, I told you, because let's say from a computer science point of view, they wouldn't have added anything to the problem. So how should one go about exploring a graph of this kind? How do you do it? Last time we represented the graph with matrices, which is somewhat the classic representation. You could very well do it with this type of graph too. That is certainly a valid option. However, when you are faced with these specific types of problems, I'll tell you right away, you might want to try an alternative approach that we can define it as the method of using lookup tables or reference tables. It is often a much more efficient way to handle these calculations, and it can really simplify the process for you. Basically, we did this in the previous video too. You can prepare the data, run it, process the data once, and then go and consult the results, keeping them ready for consultation. If data processing is too heavy or too long to be performed every time, rather than, for example, redoing the same calculations every time, it is better to do them once, save the results, and then go and consult them. In this case, it can be useful to have a database to insert into the program, let's say into the software architecture, to be more precise, to insert a database. So what I'm showing you today is a somewhat intermediate solution in the sense that the data is calculated every time the graph exploration is performed. However, when we look at the modeling of the network and therefore the structure of the graph itself, we find that instead of being based on simple tables, this time the entire system is based on a database. By utilizing this graph structure and leveraging this network, we are building a database for this project, which is a key step in our data architecture. And we will also use the facilities, in quotes, of the database, that is in particular the queries, the searches based on the database, a bit to make our work easier when we have to write the program. So essentially, we are performing a mixed operation here. We do write our own custom code, but we heavily rely on what the database already does for us to make this entire operation much simpler and more efficient. And then, in the very end, to finally complete this recipe, we add a small, careful pinch of randomness to ensure everything works as expected. I mean, in the sense that when we have to go out and look for a specific station, it's quite a process. In reality, we honestly don't know which line might be the one to cross, the specific line that can actually lead us to the solution we need. And so, since we have a computer at our disposal that is a very fast calculation tool that is capable of performing many millions of operations per second, or rather billions of operations per second, in this case we go randomly. That is, we randomly generate the possible interchange stations, and we go to see randomly which could be the line on which to search for the arrival station. So we have a mix of databases with queries on one side and random functions on the other. Let me make a quote. There is a computer scientist named Avi Wigderson who is an expert and who advocates, let's say, the use of random variables in problems that are also normally treated in a deterministic way. And I somewhat agree with him in the sense that random variables, if we consider them just once on a single problem, seem absolutely irregular, let's say indeed random, irrational. In some way, they give us an idea of irrationality. But if, on the other hand, we start thinking about complex problems, which, by the way, we can start to consider a complex system because of its complexity. And so when we find ourselves in a situation of this specific kind, if we then take a moment to look closely at the continuous and repeated use of this particular program, we begin to see that these random variables actually possess some truly absolutely important characteristics of mathematical regularity that are worth noting. For example, if I consider a random function, therefore a function that for every point has values that are absolutely uncorrelated with neighboring values, and I go to see if it is truly a random function, and I look at the spectrum of this function, the count of the values that fall within a given interval, we will see that the spectrum of this function is constant. And so we move from maximum irregularity to maximum regularity. This property of the random function can be useful to us when we face complex problems. It can be useful to us because it allows us to, in the exploration of complex systems, in fact, it allows us to work with a certain regularity. In the long run, it pays off. That's what I mean. It seems like a paradox, something counterintuitive, but in fact, it is this approach. That's why I used it. So in this video, we will see a bit graphs. We will see a bit of databases, and we will see a bit of the non-deterministic approach to problem solving. Now we've already put enough on the table, without showing you the paths time after time, because obviously I don't want to take away the pleasure of you going to check for yourselves whether the program's answers will be correct or not. Anyway, I've more or less checked them. They're fine. So why don't we take a closer look and explore how this specific database system actually functions? So yeah, more or less the things I had to tell you are those contained in these initial notes. And let's start by building the database. Obviously, it's not mandatory to build the database every time. You can just do it the first time. On the other hand, let's say to build the database, it's clear that I need to be in a slightly more complex software architecture. For this project, I need to have a reliable MySQL Server instance available and ready to use. It is essential that this database server is properly configured so that it can consistently respond to all of my incoming data queries without any issues. I personally use WAMP as my primary schema setup, which is this specific interface you see right here, WAMP. And if you look inside the WAMP environment, there is a site, technically speaking, it is a site that actually contains many different databases for us to work with. This site is named pphpMyAdmin. We will create this site here, this Paris Metro database, or let me say it the Italian way, Paris Metro, Pari Metro, whatever. So let's take a closer look at how it's actually made for now, because it is really important to see that this site must accurately represent the reality that I showed you on the map earlier. It's crucial to understand the context here. So how must it work? We have a table with the lines that contains the line number. You see, however, not all the numbers are actually numeric, and there is something important to point out here from an IT perspective. Now we'll come back to that. So it contains all the lines and they are identified with a numeric identifier. Now, what is the problem? Wait, but don't they already exist? I mean, isn't line 13 already a number? Why do I have to define it as number 11? There. So where is the problem? These here are not real numbers, they are numeric codes. The difference lies in the fact that a numeric code can easily be replaced with alphanumeric information as well. For example, if I then need a branch of line 7, I'll call it what it was called 7 bis. But this is not without consequences. While with a number I can always perform arithmetic operations on an alphanumeric code, I can perform alphanumeric type operations, very often only alphabetical ones. I can compare two strings. What are other examples, just to be clear, of numeric codes? Well, for example, a phone number is a numeric code more than a number. It's obvious, which doesn't mean that it absolutely cannot be used as a number. Some numerical operations can be performed, but normally it is only used to make comparisons. That is, to search for a number within a list, to identify as a label, as a brand, to identify a telephone line, a telephone device, or a series of telephone devices. So here we have a first table that describes to me, we can say it like this, the lines, all right? You see, the RER lines are not there. They should be added here. Then the difficulties become practical difficulties in having to add data taken from different sources. And so it becomes a, let's say, mechanical job that, let's say, in this context does not seem necessary to me. The other table is that of the stations. And here there is a list of stations without, however, specifying which line they belong to. Important in the French language is the fact that they are indeed named with names in the French language, and in the French language there are special characters. You see, the accented letters, that is why it is important to use an encoding that allows these characters to be recognized. For example, I'll say UTF-16, but I'm just giving an example. They could also be different. And it is extremely important to write the station names correctly, because if we use string comparison, string comparison is an extremely demanding operation. The strings must be formed by the same characters from the first to the last. In principle, if I add a space at the end of a string, it might not be recognized as equal to another string. Very often, comparison functions take these typos and things into account, but it's better to always be very careful about this. So we have the stations, we have the lines. The correspondence between stations and lines is done here with, at this point, only pairs, numerical pairs that put together not the name of the station, but at this point, the code. We use database technology. So the station coded as 1 is found on line 1, but I could very well write, even in another row of this table, the station coded as 2 is found on line 1, and so on. If a station belongs to multiple lines, so it's an intersection, I can very well add lines to this table. So looking at these three tables, they provide me with a robust database structure that effectively manages the core requirements, at least for the specific problem of establishing the itinerary. I believe this setup is more than sufficient for what is needed here. In fact, it really allows me to leverage the full power of the database functions, specifically those query type functions, to perform complex searches with ease. It makes the whole process much more efficient. Now that we have that foundation laid out, let's go ahead and dive into the code to see how it all comes together. Let's go to the code and see how it works. The first part of the code is used to build the database, as I told you, so it can be used only once. This is the specific file that you will find located within the GitHub repository. It is already fully prepared and pre-configured with all the necessary data regarding the stations and the various lines. Starting directly from this file, you will be able to construct a comprehensive database that accurately describes the entire Paris metro system, including all its connections and infrastructure details. So we'll do it. Let's see where we've gotten to. We're starting from 21. This will be 22. All right, obviously, if there are no errors, these cells won't print anything. Then at the end, there will simply be one to check this first part. You need to launch WAMP. I've already done that. It's clear that we need to have a database. We need to have I told you, a MySQL server ready to respond. And this is being done. We could go and check, actually, let's do it, that in the database, let's see a bit. Here it is. If I refresh it, it takes a little while. There, looking at this database, at the moment, it only contains the stations table. This is because the previous data was completely destroyed. It was accidentally deleted by the program. Although it was subsequently rebuilt, it is currently only a partial recovery because, as you can see, there is only the stations table present. So let's go ahead and rebuild the lines table, and then we will also proceed to rebuild the line stations table to complete the set. Okay? So now we have rebuilt the database. Let's do a test. This is just for verification. Good. The important thing is that there are no errors. It's not essential. Let's start with the second part.